All right, Toast, thanks for the introduction. I was just thinking the only person who's not here who can speak intelligently about Mark Fassbender's work is Mark Fassbender. Anybody who has any questions about that, he's got this paper that was published last year and another one coming out any day now in economic geology on this work that Toast had already introduced. So Metal Oceans got its start about 5 years ago because it was clear that modern ocean crust was going to be compared to greenstone belt crust in some way, and we really didn't know what aspect of the modern ocean floor would be compared to greenstone belts. Yesterday and today we've heard about terrain boundaries, we've heard about assemblage boundaries, we've heard about greenstone belts of different size from 600 kilometers down to 50 kilometers. What are all those things and what do they look like in an undisturbed environment? And that's really what Metal Oceans is all about. Personally, I spent 5 years in Germany during the inception of this project because that's where the ships are. And we spent literally a year at sea exploring a number of different environments, and most of my group has participated in that activity. So I'm just going to give a brief introduction to that, and then Alan and Aaron and Chris are going to talk about the first forays into comparisons with greenstone belts of the type of work that Taus was talking about. There's the group. It's expanded and contracted several times. We're now down to the core, who is really trying to take the work of quite a number of people over the last 5 years and distill it down into something that we can really compare to greenstone belt environments. We do have some stuff on the GeoHub, but we have a portfolio of about 10 different papers and student theses that are now being prepared for GeoHub. We have to talk to Ross about how we're going to put it in there so it doesn't get polluted by all the Archean stuff, but I'll let him figure that out. We've also had a number of partners, and those partners have included principally institutions that have supported seagoing activities, in particular our German partners, Geomar. They've all now been collapsed into another program which is sort of running in parallel to Metal Earth, and that's the Image Create program, which focuses on training in geodynamics and georesources. You can go to the website and see what that's all about, but it's really an integral part of Metal Earth. Ross is on the board. So what's the progress in Metal Oceans? We started out with a compilation and the very first 1-to-1 million scale geological map of the Lau Basin, which I think many of you have seen. That was published in 2022, and that work is now pretty much completed, and there are a few more papers, and especially some monograph to capture all the work that the graduate students did, especially the master students who did really spectacular mapping at 1 to 100,000 scale, 1 to 200,000 scale. Our first map was 1 to 1 million scale. We're now currently, or Alan at least, is currently completing a project on SIN to post-collisional extension, which is happening in eastern Papua New Guinea, and that map was completed last year by Philip Brandel and will be published shortly. And this is a different environment, and Alan will talk about that a little bit at the end, and I think he's talked about it in November as well when I was at sea. The final sort of a triumvirate of the areas that we're working in the interest of developing a portfolio of things to compare is ridge hotspot intersections, and a number of us just came back from Galapagos in November where we had the opportunity to map really one of the best submarine examples of a ridge hotspot intersection as a potential analog for some environments. What are we doing in all of these places? We're basically comparing or examining how microplate architecture, which we think is fundamental to what we're studying at least, how this works in the framework of crustal growth in these different settings, and then ultimately can we recognize that in the geological record. There are two things that underpin the project from an endowment point of view, and the first one is this obvious plot here that has been in prep now for, I don't know, 5 years, I think. I got to get this out, but it's a simple plot of the distribution of VMS deposits through geological time, which obviously correlates with big episodes of crustal growth. and the black dots and represent the occurrence of VMS deposits. This collection here is almost entirely in the Abitibi. The problem with this relationship is that we understand crustal growth at a very broad scale, 50 to even 100 million year timescales, whereas the timescales for the growth, for the formation of individual VMS deposits are more like short bursts of crustal growth, not these long episodes of crustal growth. So we want to know what that looks like. How can we recognize those short bursts of crustal growth? And secondly, there's maybe even a more important thing, which often I think gets forgotten, and that is that VMS deposits, of course, correlate with these pulses of crustal growth. They appear to be byproducts of these pulses of crustal growth, but in fact, they're an essential requirement of the microplate mosaic and the microplate growth, because the hydrothermal activity that makes VMS deposits cools the crust. And you cannot have microplates spreading any other tectonic activity without VMS deposits to some degree, because the hydrothermal activity cools the crust. And it stands to reason that if the hydrothermal activity cools the crust, the more spreading centers, the more ridges, the more plates you have separating from each other and exposing mantle, the more massive sulfide deposits you're going to have. And this probably peaked, you all know this probably peaked in the late Archean when mantle temperatures were 150, 200 degrees hotter than they are today. And as a result of that, or one way to deal with that, to accommodate that high heat flux, is to have an Earth that was covered by many small plates. And the more small plates you have, the more spreading ridges you have, and the longer the total spreading length, and the more efficient the cooling. It's pretty simple. And this functions at the global scale, and it functions, I think, at the greenstone belt scale. And that's one of the things that we want to explore now. We have no answers to these questions at the moment, and that is, to what degree can a microplate model explain some of the lithostratigraphic relationships in terms of assemblages, and then explain some of the structures in terms of the evolution and the growth of greenstone belts. So we chose as our first example, and I'm going to talk a little bit about this because it's the one we know the most about right now, of the Lau Basin as an area to learn. What is a plate boundary? What is a microplate boundary? How does extension occur? How does crustal growth occur? And we zeroed in on this central northern part of the Lau Basin in the Western Pacific to address sort of four major questions. First of all, what does a pulse of crustal growth look like? What are the probable time and space scales? Can we recognize mantle anomalies that may be associated with those short bursts of crustal growth? And what types of ancestral structures might have been important for controlling all of those processes, plus the consequential mineral endowment? I spend a lot of time thinking about what are people thinking when they tell me about terrain boundaries or plate boundaries or assemblage boundaries. What scale are they thinking at? And I spent a lot of time hammering that, well, this is the scale we're talking about. We can take the entirety of the Abitibi greenstone belt and fit it in our study area. For example, the distance from Kidd Creek across the Destor-Porcupine Fault Zone through the Blake River Group into Val-d'Or and up to Chibougamau. That's basically the scale that we have been working at. And so many of the things that I hear are at a different scale. The great thing about the Abitibi, or rather about the Lau Basin also, is that as we've just heard about Mark Fassbinder's work, it's petrologically very complex. I'll mention that in a minute. And from a modeling point of view, you can put as much subduction zone or as much arc into this model as you want simply by moving the Abitibi greenstone belt back and forth from something that has lots of subduction signature and lots of arc to something that virtually has no arc signature or very difficult to recognize an arc signature at all, even though you're obviously in a subduction zone. A couple of definitions maybe are worth touching on. We can look at Bird's definition of a microplate from 2003. His definition of a microplate globally was simply a small, mostly rigid, that's very important, mostly rigid, not completely, mostly rigid areas of lithosphere that are located at major plate boundaries but they behave as independent plates. And in Bird's original definition, this was anything that was smaller than 1,000 kilometers by 1,000 kilometers. So that's pretty big. What you're going to see is that, in fact, microplates are, and what we now call nanoplates, are recognizable down to 50 or 100 kilometers in size, starting to get to that granular character of greenstone belts. We chose the Lau Basin as our first area to try and explore this because it's a spectacularly well-endowed region of the Earth with many of the world's large copper and gold deposits. It's the fastest growing crust on the planet right now, and it's the hottest. The mantle temperatures are predicted from shear wave velocities, and the red dashed line that you see right here is basically the data at down to 100 kilometers for the Lau Basin. These other lines are other places in the Pacific. Predicted mantle temperatures are at least 1,450 degrees, maybe 1,500 degrees, and hottest place in the Pacific. If there is anywhere on Earth today that is a modern analog of a hot Archean mantle, this is it. And so that's why we went there. But again, I want to get back to scale. So the Lau Basin shown here between New Zealand and Papua New Guinea is only a part of the regional Indo-Australian margin. And the regional Indo-Australian margin is probably something more like Superior Province in scale. So the entirety of the Lau Basin from New Zealand to Samoa would fit within the Southern Superior Province, the whole of the Southern Superior Province. The Lau Basin, or rather the Abitibi Greenstone Belt, which is indicated by these green silhouettes here, well, you can get any number of those in any one of these small back arc basins along the entire length of the terrain, or rather the entire length of what we call the Lau Province. The terrain boundaries, which we talked a little bit about on Wednesday, these are the big structures, these are the big subduction zones that penetrate in this case 20, 30 kilometers at most, 10 to 15 kilometers to the Moho. And the microplate boundaries that we talk about in the context of a greenstone belt scale are really the spreading centers and the transcurrent fault zones that occur within individual back arc basins. This is the map that started everything for us. We had to learn how to do this. Meg Stewart was the lead on that, and she published this with the whole group in 2022. And what separates this map apart from anything that had ever been done before in the ocean was a very careful formation legend with about 40 different formations that were distilled into about 20 different assemblages. Exactly the same terminology and exactly the same thinking that goes into the assemblage maps and the formation maps that we've seen in the Abitibi Greenstone Belt. The difference being that we're really focused on these small features shown in orange here, which are the spreading centers at the edges of microplates. What distinguishes a microplate from just a tectonic block? They're structural blocks. What distinguishes them is that the plates are growing, and they're growing at spreading centers that are on at least one side of your typical microplate. In addition to the geological maps that we now had to work with, as Taos already pointed out, we're now able, for the first time ever, because so many samples are being collected, we're able to paint these maps with geochemistry like we never could before. And this is some of the work, early work that Mark Fassbender did, identifying really dramatically variable volcanic rock compositions, in this case felsic volcanic rocks, within the Lau Basin, back arc basin, ranging from typical arc-like signatures to typical mid-ocean ridge-like signatures to typical ocean island basalts, all on top of each other. Mark's, I think personally, because I'm not a petrologist, but I think Mark's best contribution was the tool that he developed, which was a machine learning classification tool, and Taos alluded to the target classes, and he basically was able to take all of the felsic rocks on the modern ocean floor and use them to train a tool for classification of different environments. And that paper is published. This is the data, or this is the forthcoming data on the mafic volcanic rocks, which illustrate how these classes of different, and these are classed by tectonic setting, can be closely juxtaposed within the framework of even a small area like the Northern Lau Basin. And this map shows the Northern Lau Basin with many of the spreading centers and the associated volcanic rocks having bulk compositions that range anywhere from rocks with enriched mantle sources to depleted mantle sources to subduction-related signatures to plume signatures, in some cases 10 kilometers apart, in some cases even closer. So that was Mark's, so that sort of sets the framework for, we have now a geological map and we have the petrological data set to try and do the kinds of comparisons that are already being done here in the Abitibian and other Archean greenstone belts. But our first task was in fact to repeat or to duplicate a metal earth transect across the plate margin of what's known as the Nuafo'o microplate right in the middle of the Lau Basin. And that was done with a series of transects, seismic transects and multi-parameter geophysics. 6 of them that range in length from about 100 kilometers across to about 300 kilometers across, in this case from the eastern edge of the Nuafo'o microplate, which is a rift called the Fonolai Rift, to the western edge of the Nuafo'o microplate, which is, I'll show you later, a very large transcurrent fault zone called Peggy Ridge. These, I've already talked about the seismic sections in previous meetings, so I'm not going to dwell on that, but I will emphasize these are just 3 examples. We imaged the crust down to 7 kilometers using reflection seismics and down to about 20 kilometers or more using refraction seismics. What distinguishes this work from a lot of other work in the Western Pacific is that the vast majority of seismic surveys have been performed at the arc front. They're looking for the slab. And that's not what we were interested in at all. We were interested in the entire back arc region, which is where most of the crustal growth actually occurs. It doesn't occur at the arc as much as it does at least in the VMS hosting environment. Occurs mostly in the back arc region. This is one of the typical sections, one of our longest sections across the Nuafo'o microplate. There's the eastern boundary, which is called the Fonolai Rift and Spreading Center. But in fact, what we've determined from the seismic surveys is that the boundary of the microplate is diffuse. It's not a fault. It's not even a single spreading center. It's multiple spreading centers that are constantly jumping, in this case, jumping from west to east. And each time it jumps, it fills up another small sedimentary basin. There's 100 kilometers for scale for the middle part of this section. So the boundary of the microplate, this is why we say they're somewhat non-rigid, is really a deformation zone. And it's infilled with volcaniclastic sediments. It includes relics of arc crust in the middle of a back arc basin that have nothing to do with the crust that it's currently on. And then finally into back arc basin crust. These sedimentary basins we just started working on. We had one student who did a really spectacular job on this, and they're intruded by melts, so that's the ongoing rifting or ongoing spreading within this transitional zone. And we even found, or she even found, what looked to be hydrothermal upflow zones buried under 100 meters or so of sediment. So that's what the microplate boundary looks like. It doesn't look like a boundary at all. It looks like a deformation zone. However, on the other side of the microplate, we do have a fantastic through-going, maybe even crustal scale fault, steeply dipping, that is, for a large part of the system, a transcurrent fault. This is the seismic refraction data underneath the Nuafo'o microplate. There's the Fonolai Rift on one side of the microplate, and there's the Peggy Ridge transform on the other side of the microplate, and this is the refraction seismics underneath, which show an undulating mantle at a depth of about 10 to 15 kilometers below the microplate, with basically an upwelling zone under the microplate, and an excursion in the Moho at exactly the Fonolai Rift boundary or boundary zone. And this is the same data shown a little without the three-dimensional perspective. And there we're looking at a 5-kilometer high excursion in the mantle immediately under the margin of the microplate, and then about 140 kilometers of mantle upwelling until you get to the other end of the microplate. So in my mind, these microplates are to a large degree mimicking mantle domains at this scale within the northern Lao Basin. Those data are converted to densities here, and you can see the compositional variability within the lower, especially the lower part of the crust. If you go back to this one, you can see how irregular those velocities are in the lower part of the crust. We did manage a magnetotelluric survey of 40 days deploying ocean bottom magnetotelluric sensors, and we deployed them immediately over the Fonolai Rift. I can say that this is extremely rare data. Nobody's really ever done this before in a back arc or in any kind of volcanic arc environment. And don't really know how to interpret this except to say that we see strong, steeply dipping conductors. And they appear to be plate boundaries or marking the plate boundary. We only had one deployment, so we weren't able to instrument other plate boundaries that we would have liked to have instrument and see if that's really a common feature of those boundaries. The gravities, we had countless days of ship-based gravity measurements. The Bugey gravity clearly shows, there's the Nuafo'o microplate where the cursor is. It clearly shows the rifting and the upwelling of the mantle underneath the Fonolai rift boundary. It clearly, in my mind, shows a new boundary which is emerging at the southern end of the Nuafo'o microplate that we can't see on the seafloor. We see it in the gravity, but we can't actually see any physical manifestation of that on the seafloor. Chris Galley, who's going to report on this work in a couple of minutes, has been doing gravity inversions that have been really spectacular. This is a gravity inversion of the southern tip of the Fonolai Rift. That's 10 kilometers for scale right there. This is the crustal thickness inversion that he's done, and you can clearly see the thinning of the crust and the V-shaped opening of the rift as it propagates into arc crust. You can also see that it's actually splitting at the bottom at the southern tip of the Fonolai Rift, and that's probably an emerging triple junction with a strong density variation related to mafic intrusive rocks. Chris has done the whole of the Lao Basin this way, and I think this is one of the best developments we've had in the last little while because it shows just how granular, this is crustal thickness inverted from regional satellite-based gravity. It just shows how granular the microplate architecture can be. With a scale down here of 200 kilometers, you can see there's the Fonolai Rift. There's what could be a buried rift that we are currently not. This is the only data we have, but it could be the emergence of a new microplate boundary at the southern end of Nuafo'o. We're also able to use the gravity to refine our assemblage mapping. So most of the mapping, the geological mapping, was recognizing formations, and we wanted to group those into assemblages just like you would in a geological map of the Superior Province. And this was done using, in part, done using gravity to separate different types of crust. And that's basically what assemblages are. They're different types of crust. And this is the assemblage map for the northern part of the Lao Basin, which shows older crust in brown and gray, more recent crust in dark green, and then a very recent pulse of young crust within the last 5 million years in light shades of green. These pulses of crustal growth are making volcanic assemblages, but they coincide with a microplate breakout. So what's the relationship between, in our world, what's the relationship between microplates and assemblages? Microplates are easy to map on the modern ocean floor because each microplate, scale for 200 kilometers up in the corner there, each microplate is bound by a wide range of different mappable features: back arc spreading centers, ridge transform boundaries, extensional transform zones, leaky transform zones, triple junctions, overlapping spreading centers, plume-driven spreading centers. It goes on, and every color that you see here is demarcating about 7 microplates. So we actually went from early studies in this region from 3 microplates to at least 7 now. And they're all bound by spreading centers, in part, and by very large-scale transcurrent faults, because you need this transcurrent motion to allow for the growth of the basin, in this case 400, 500 kilometers wide in 5 million years. You have to accommodate that with some strike-slip faults. Those are the strike-slip faults. These were mapped by Alan Baxter using seismic activity. And you can see that the entire basin is bound by a very large transcurrent fault zone up in the north, which is called the Futuna Deformation Zone, and a very large transcurrent fault zone in the south, which is called the Peggy Ridge. And those are the highways along which this crustal growth can occur. So we have microplates, which are structures, and we have assemblages, which are volcanic formations. And the relationship between them, I think this is a relevant story for mapping assemblages and formations in greenstone belts. The relationship between those two is not always obvious. But it becomes clear when you overlay the microplates. These are in the shaded greens and browns. These are the larger of the microplates within the northern Lau Basin, overlaying on the assemblage map. And you can see in the background these gray zones. There's a triangular shaped gray zone right there, which is the phonoli assemblage. Those are lithostratigraphic assemblages. And you can see that they emerge, the phonoli assemblage emerges from a plate boundary, a spreading center, which runs right down the middle of the assemblage. Half of the assemblage is accreted onto the North Tonga plate, and the other half of the assemblage is accreted onto the Nuufo'o microplate. What this means is that microplates are made up of many assemblages, pieces of many assemblages. That, I think, is going to be important, at least for the work that we're going to do. The thing is that it's easy in the modern record to see the microplates. It's really difficult to see them in a greenstone belt. But we think we have some tools, and one tool is triple junctions. It's a requirement of plate fragmentation, which is what microplates are. It's a requirement of plate fragmentation that for every new microplate, you make 2 triple junctions. And you can see them on here. In some cases, in the case of the Futuna microplate, we've got 5 triple junctions. It's not just a microplate factory, though. This phenomena is a triple junction factory. Can we use triple junctions to identify, or can we use our knowledge of triple junctions in the modern ocean floor to identify triple junctions and therefore microplates in greenstone belts? I don't know. We have many maps like this now. This is a very good map of a triple junction. There's 40 kilometers for scale in the North Fiji Basin. And the first thing you notice about triple junctions, which took a little, it wasn't so obvious at the beginning, is that they're big. This triple junction has a footprint, a structural and magmatic footprint that's at least 100 kilometers long and about 50 kilometers wide. You can't put your finger on a fault intersection somewhere in the Blake River Group and point to it and say that's a triple junction. They're not triple junctions at a point, or they're not triple points. They are districts, whole districts. So in fact, you've got something on the order, and not only structural districts, but magmatic centers, because obviously you've got crustal permeability that is going to allow melt to accumulate in large amounts. So several hundreds, I think in the case of the North Fiji Basin triple junction, something like 300 or 400 cubic kilometers of melt erupted exactly at the confluence of the 3 spreading centers. And if you overlay that on the eastern Blake River Group, just like at the same scale, you bury the whole Blake River Group. Maybe the Blake River Group is a triple junction. Here's another one in the Lau Basin itself. This one is 600 cubic kilometers of melt. One of the limbs of the triple junction outgrew all the others, but it's a massive amount of melt that again, once again, would cover the whole of the eastern Blake River Group. Coming to the end here, Ross. He keeps looking at his watch, so. Which not because he wants to know how much time I got left, he just wants to make me nervous. There are ways to map triple junctions, and Erin's going to talk about this in a moment, and she's been doing lineament analysis, similar to what Jeff Harris has talked about, but in a kind of a different way, and she's mapped the density of intersecting lineaments in the northern part of the Lau Basin. And this heat map, actually it's a little bit offset, but this heat map actually picks up all the triple junctions pretty well at a scale of tens of kilometers. And the question is, could this approach work? Something we're going to be exploring. Not from a mineral prospectivity point of view, but rather from a microplate / triple junction scenario. What would that look like if you, after north-south shortening and east-west stretching? Well, in my books, it would look a lot like this, notwithstanding the history of all of these faults. And that's something that we hope to look into in the coming year or so. Last slide, second last slide. We heard a lot about crustal growth as a consequence of heat and enhanced heat and crustal permeability in greenstone belts. I mean, for me, it's pretty obvious, and we talked about this briefly on Wednesday, that the Abitibi is somehow off scale in terms of the total area of volcanic rocks compared to the Wabigoon and North Caribou. The first thing you say is, well, that's just preservation, which is probably true. But there's this other issue which just came up in the last couple of talks, is that, well, there's maybe 2 or 3 times as much volcanic rock in the Abitibi, but there's at least 10 times as much massive sulfide deposits. So it's hard to explain that difference away simply by preservation as opposed to productivity. And finally, I think that comparison, this also came up a couple of days ago, that comparison is something that could be carried to other cratons. And I'll leave you with this final statistic before I get Aaron and Chris and Ellen up here, about VMS deposits in Archean greenstone belts. We know, this is from Pat, we know of about 150 Archean VMS deposits worldwide. There are about 30 of them in Western Australia. There are 1 or 2 in the North China Craton. Maybe there's one in Guyana. What's that? That's 33. All the rest are in the Abitibi Greenstone Belt. So there's clearly something different that needs to be resolved. I hope we're getting there. And what we're going to try in Metal Oceans is to sort of refine some of the ideas by looking at real things and undeformed structures on the seafloor. Okay. Yeah, that's great. We can have a discussion.